Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to give you motivation for a very, very important topic in mathematics known as category theory. Now, one way to think about category theory is that it's a type of second order abstraction. Okay, so what do I mean by that? Well, I guess one way to see this is, let's look first at what do I mean by a first order abstraction. Okay, so let's take, for example, the notion of a group. So what are examples of groups? Well, examples of groups include things like permutation groups on one hand, matrix groups. You also have the additive group of integers. And what group theory does is it ties together all the common principles in all these examples and looks at them together. So it abstracts the basic properties in these examples so that you can study them in the same way, okay? Let's look at another mathematical notion, that of a topological space. Okay, so examples of these include things like Euclidean space and also spaces of functions. Okay, and the point of a topological space is that it abstracts the common principles so you can talk about continuity in these cases. Okay, so that's first order abstraction. But where category theory comes in is if you want to take one branch of mathematics and you want to use it to study another branch of mathematics. For example, if you want to use algebra to study topology. Okay, so in this case, what you want to do is you want to think, well, when you're studying algebra, what are the common themes there to when you study something like topology? And that's where you need to look at a second order abstraction. So category theory abstracts on the second level. Okay, so let's start with the board here and see some ways that category theory is used. Okay, as I said, it's used when you want to use one branch of mathematics to study another. And the first one that one usually meets, which is extremely interesting, is it's used in studying topology by using algebra. In fact, you use algebraic invariants to study topology, and algebraic invariants include things such as the cohomology groups, but there are lots of others as well, including K-theory and the fundamental group. Another example is, suppose you want to look at module theory, the study of modules over a ring like the matrix ring, which is n by n matrices over some field K. Okay, so this is a very, very interesting problem to try to look at the modules over this. And it turns out that you can use category theory to reduce the study of this module theory to just studying vector spaces over K, which is something that we're extremely familiar with. Okay, and the list can go on ad infinitum. There are lots and lots of examples like this. And in this video, I want to give a very simple example, which is hopefully one that's not familiar to everyone. It's about the invariant base number. Okay, so let me show you how that happens. So basically, I want to motivate this category theory by looking at this little example, which shows you how you can cross over from one branch of mathematics to another branch. We're going to start with the ring R, and what we're going to do is we want to look at the module theory over this. Okay, and we're going to say that the invariant base number property holds for R, so I'll just abbreviate that as IBN. This holds for R if whenever you have an isomorphism like this, m copies of R is isomorphic to n copies of R, then you must have m equal to n. Okay, so let's just look at this property for a little while and make sure you have some sort of feel for what goes on here. Suppose R is just a field. So if R is just a field, then here you just have m copies of this field, so that's just an m-dimensional vector space. Here you have n copies of the field, that's an n-dimensional vector space. And of course, if these are isomorphic vector spaces, then the dimensions have to be the same, so m equals n. And so you may think from this example here that of course, this should hold for every ring R. So that's the natural question. Does the invariant base number property always hold? And let me give you the answer to that, which makes it interesting. It turns out that the answer to that in general is no. Okay, that's rather surprising perhaps. Okay, I won't give you the counterexample. It's quite interesting to try to find one, but let me show you what you can prove, okay, in this theorem over here. Suppose now that R is commutative. I claim that in this case, then the invariant base number property does in fact hold for R. And I'll actually show you how to prove that. And the way we're going to do that is we're going to study R modules by reducing it down to modules over a field, which just means vector spaces over a field. Okay, so that's the way I want to cross over from the theory of R modules to modules over some field. Okay, so let me show you how that works. So how do I pass to a field, and what is that field that I pass to? So what I'm going to do is I'm going to pick I to be any maximal ideal inside this commutative ring R. Okay, Now, of course, for the existence of such a maximal ideal, you need Zorn's lemma. Okay, so we're going to pick such a maximal ideal. And the point of it being a maximal ideal inside a commutative ring means that when I look at the quotient R mod I, this is now a field. Okay, so that's the field that I want to play around with. And I want to relate modules, particularly free modules like the ones here, to vector spaces over this field here. Okay, so K is a field, and now I need to introduce some ideas. And the important idea here is the notion of a functor. And the functor here, I'll abbreviate it to F in this particular video, but in general, you see it in the literature, you'll see it as a tensor product, so it's a tensor functor, K tensor R blank, okay, and the blank here stands for some R module M, okay. So the way I want to tell you about categories is the following. I want to tell you about an example of a functor, okay. So when you learn about vector spaces, for example, just to give you an analogy of how I want to explain what's going on here, when you learn about the linear algebra, sometimes it's actually easier to understand linear functions, okay? There are lots of examples of linear functions that you're familiar with, and once you have a good understanding of that, you can talk about what vector spaces are. So I want to do a similar thing here. Sometimes the morphisms are actually easy to understand, and then once you understand or get a feel for some examples of the morphisms, you can talk about the objects themselves. So later on, in the next video, we'll talk about categories themselves, okay? And the functors will be like morphisms between the categories. Okay, so I just want to give you an example of a morphism between categories. Okay, and it's going to be a way to connect R modules on one hand to vector spaces over this field K in another. Okay, so the way we'll do that, it's going to be set up using this proposition definition here. Okay, so the first thing is that we have this ideal R, I, and we can look at this R submodule IM. Okay, so I claim here I'm going to define an I submodule. It's basically just I linear combinations of elements inside M. So formal linear combinations, we form all these linear combinations, sum of Ri, Mi, where all the coefficients Ri, these scalars are inside our ideal, not ranging through all of R, and these Mi's can range over all the elements inside this module M. Okay, so certainly all these elements are inside M, and it's quite easy to see that this is an R submodule of M. If you sum two such objects, of course it stays inside here, okay, and of course you'll get a subgroup of the additive structure. You take negatives as well, and if you also decide to multiply by scalars inside R, since all these Ri's are inside I, that's an ideal. You can multiply things by here by R, and it stays inside I. So if you multiply by a scalar in I, you still get an I linear combination of elements inside M. So we see quite quickly that this IM is indeed an R submodule of M. Okay, so what's the module over K that we're interested in? Okay, so firstly I want to construct an R module. You have an R submodule, so you can look at the quotient. So we're going to look at M mod IM. There's the quotient. Okay, so that's what I'm going to denote by this K tensor Rm. This symbol here being the tensor symbol. And here we'll abbreviate this to just Fm. Okay, so this is just for this video, I use this abbreviation, but this is the standard sort of notation for this object over here. Okay, so I claim that it is an R module, but actually it can be viewed as a vector space over K. Okay, so how do we do that? Okay, how can we view it as a vector space over K? Well, this is an R module, so it has an additive structure. Okay, so it's an abelian group. And the only thing now we need to do is we need to say, if we're given an element inside this M mod IM, so that's something like this one here, this M plus this IM, a coset like that, we can scalar multiply by elements inside K. And remember, K is this quotient R mod I, so it's of the form alpha plus I, okay, coset of I like that. Okay, so remember one thing we can do is that we can multiply, this is an R module, okay, so we can multiply by alpha. Okay, so this here has to be an element of this. Okay, we want to scalar multiply by elements inside this field K now, and the answer to this is it's a coset of IM, and which coset is it? It's the coset of alpha M. Okay, so that's what we will choose. Okay, so that's very well and good, and this is a very, very natural choice, as you can see. So this alpha will be inside R. So essentially it's just induced by the R module structure on this quotient here. Okay, this one here. And the only thing that you really need to check now is that is this independent of the choice of representatives alpha and m? Okay, so firstly, it's independent of the choice of the representative m here, and that's because, well, that's just the R module structure. You have an induced R module structure on this. So if you understand this is an R module, then this is then you understand this is independent of the choice of coset representative here. You also have to check that it's independent of the choice of coset representative here. So if you change this alpha by some element inside I, okay, so let's throw in an extra. Suppose we change it by some alpha prime inside there, inside I, then of course how does this change? You've got an extra alpha prime m. But that alpha prime m, since alpha prime is in I, that's inside here. So it doesn't change this coset. So this is well defined. And it's quite easy to see that because this is an R module, so you can check the distributive law and all those other module axioms, that this is also a vector space over K. So in that way, we have gone from an R module M to this M mod IM, which is first an R module, but now we've seen we can actually view it as a vector space over K. And that's our functor K tensor, which allows us to pass from this R module to this vector space over K. Okay, so let's look at an example of one of these tensor products. Okay, so let's feed in the R module R to the N, this free module here, and see what K tensor R of Rn is. Okay, so let's see how that works. So remember, we start with the module itself, okay, and that's the set of all n tuples, R1 to Rn, where all these Ri's are inside R. And then what we'll do is we look at this and we look at all I linear combinations of elements inside here, I times this thing. It's quite easy to see that if you take I linear combinations of things inside here, the only n tuples you can get have coordinates always inside I. In fact, you can find any n tuple, all of whose coordinates are inside I. All these turn out to be I linear combinations of things inside here. In fact, you can take the linear combination J1 times the first basis vector plus J2 times the second basis vector, okay, and so forth, down to Jn to get this particular element here. So basically, now you've got this R submodule of this R module here, and this tensor product is just a quotient of these two. And it's quite easy to see, of course, what this has to be. Okay, so this is a vector space over the field K, and I want to show you what that is. So what's the data of giving an n tuple modulo this submodule here? So really all you need to do is give me an R1 modulo all these J1, so an R1 mod I, and an R2 mod I, and an R3 mod I, and so forth. So basically you're giving me an n tuple of elements inside R mod I. In other words, an element of K to the n. So we see in this way, rather nicely, that when we apply this functor K tensor R to this R to the n, we just get K to the n. Okay, that's a very, very nice result here. And that's a very, very natural sort of a thing. Okay, so we've seen a way where you can pass from an M module, you input an M module, and it spits out a vector space over K. The next thing we want to do is to see a similar passage from R module homomorphisms to K linear maps. Okay, so let's see how that works. Suppose now M and N are R modules and phi is some R module homomorphism between them. Okay, so what we can do is we can look at Fm, which is a vector space over K, and Fn, which is a vector space over K. And what is the thing we want to show now is that you can also define a linear map that's associated to this phi here. You can apply F to this phi as well. So this is F phi, which is also denoted in the standard way by K tensor R of phi. There's a linear map from this Fm to this Fn. And how does it work? Let me show you. So remember, what's Fm? That's just M mod Im. What's Fn? That's just N mod In. So let's take an input here, which is a coset of Im, say little m plus Im. And we want to send it over here. And of course, this should use the original R module homomorphism phi here. So we'll just apply phi to the only thing inside M we see, phi of m. And that lands you inside n. So you can get a coset of In and hence an element of this Fn over here. Okay. So let's check firstly that this is well defined. Okay. Of course, you could change this representative m around by something inside here. Okay. And then that change in this value here will be something inside phi of Im. But what about phi of Im? Well, this, remember, phi is an R module homomorphism, so the I can be pulled out. So this is contained inside I of phi m. And the key point is that this phi of m is inside n, so this is inside In, like that. So changing by something inside here does not change the coset of In that you're living inside. So this is now well defined. And it's quite easy to check, of course, that this is it is additive, and also it preserves scalar multiplication. So this actually gives you a k-linear map. Okay, so now we found that not only does this functor, what does it do? You can input an R module and it spits out a vector space over K. But if you have a morphism between R modules and R linear map like that, you spit out a k-linear map between the corresponding vector spaces over K. Okay, so we've introduced this, what I call a functor f here, and the most important property is what's called functoriality, and I want to talk about that now. Okay, so let's look at the very simple example where this phi is just the identity map on some module M. F is the identity map, f of the identity map on M. Okay, so what type of object is this? When you apply f to it, you apply f to an R linear map, you get a k linear map. And what's the k linear map? It has to go from fm to fm, f of this m to f of this m here, like that. Okay, and of course the natural thing that you'd hope for is that this is just the identity, and in fact that is the case. Okay, so you can see if m equals n here, okay, and phi is the identity, it just says m plus im to m plus im here. So that is the identity map. So another way of saying that is that if you have the identity on M, you can apply f to this identity on M, and it's an identity map, it's an identity on a vector space, and the vector space is Fm. Okay, so that's what you see there. So that's the first key property, which looks really banal, okay, and it's very simple to see, but it's actually very important, as we'll see in a moment. Okay, so let's look at the next property, B. Okay, and this is one that you get when you have a composite of two R linear maps, psi and phi. Okay, so let's see what happens. So I'm going to give you two ways of going from the vector space FL to the vector space Fn. Okay, so the first thing is you can compose these maps and look at phi psi, and that's an R linear map from L to N. So you can apply f to that R linear map to get a K linear map, and it's a K linear map from FL to Fn. Okay, that's f of phi composed psi. So the other way you can do it is you can split it up into two goes. You can apply phi f to this psi first. F of psi goes from FL to Fn, f of psi here. And then you can go from Fm to Fn. And how does that work? You apply f to this phi here to go from Fm to Fn. And then you can compose these k-linear maps to get a new k-linear map. And these two k-linear maps are the same. Okay, so let's just check why this is true. Okay, what we'll do is we'll just input something in FL and see that they send them to the same place. So L plus IL, where does that f psi send it to? You just apply psi to this representative here. Okay, that's how this works. Okay, how do you look at f of some linear map? You just apply the linear map to a coset representative here. So you have psi of L, the coset of that. And then you apply f of phi to that, so you apply phi to this coset representative. So it's phi of psi of L plus In. Okay, so if you were to go directly using this, what you do is to this coset representative, you apply the composite phi psi of L, and you get the corresponding coset. Okay, so you get the both, in both cases, you get the same answer, so these two maps are the same. So one way to say this is that f is multiplicative. Okay, so it looks like the usual thing you see with a group homomorphism. F of phi psi is f of phi composed f of psi, like that. Okay, so you can apply f to each of the factors and compose them. Okay, so now with these key properties, we actually have everything we need to prove the basic theorem. Okay, that if you have a commutative ring R, then it has the invariant base number property. Okay, so let me remind you what that means. Suppose phi is an isomorphism, an R linear isomorphism from Rm to Rn. Then we want to show that M actually has to equal N. So the base number here of this one is M, the base number here is N. And to say it's invariant means that if they're isomorphic, they are the same, that invariant is the same. So hence the name invariant base number. So the way we're going to do is we're going to reduce it to the corresponding property for vector spaces. So we're going to use this f functor here, this K tensor of R, okay, that corresponds to some maximal ideal, it doesn't really matter which one, some maximal ideal I of this R. Okay, so let's have a look at that. I claim all you need to do is to show that f phi, okay, so what's f phi? This is going to be, this was an R linear map, so now you get a K linear map from f of the domain, f of Rm, which we saw by this example, is just k to the m. Going to f of the codomain, frn, which is just k to the n. So you have this map here, okay? We just have to show that this is an isomorphism in the category of vector spaces. In other words, an isomorphism of vector spaces. Because we know from dimension theory for vector spaces that if km is isomorphic to kn, of course, you must have m equal to n. Okay, so that's something that we know straight away. Okay, so why is this an isomorphism of vector spaces? Well, it's actually very easy to see. And the way we'll do is we'll actually construct the inverse isomorphism here. And how do we do that? Well, phi is an isomorphism, so it has an inverse, which is an R linear homomorphism from Rn to Rm, F inverse. And now we can apply F to that to get you a K linear map from F of Rn, which is K to the n, back to K to the m. F phi inverse. And I claim it's just the inverse of this f phi. And it's actually very, very easy to see why that's true. Okay, to check that it's the inverse, you just need to compose with the original and check that the composite is the identity. So let's do f phi composed with f phi inverse. So remember by property B here, this functoriality property B here, this composite of f's is going to be just f of the composite. F of phi composed f phi inverse. Of course, phi composed phi inverse. Now, these are inverses of each other, and phi was here. So this is just the identity on Rn. So you just have f of the identity. And what does property A say of functoriality? F of the identity is just the identity on the corresponding thing. So this is just the identity on f of Rn, and f of Rn is Kn here. And I hope you can see, you can just swap the order of these and do exactly the same argument using property B and property A in a slightly different setting. Okay, but that will show that phi f inverse composed with phi, or rather f of phi inverse composed with f of phi is equal to the identity on k to the m. So indeed, f phi inverse is the inverse of f phi. These are isomorphic vector spaces, so m equals n, and the invariant base number property holds for the commutative ring R as well. Okay, so I hope you like that proof. It's really neat, and it's based on a very, very simple idea here. Okay, the computations here are very short, but of course you have to set up this theory of this functor. Okay, so really the key to the proof of this whole thing is the functoriality A and B. And what's a category? Okay, so the category theory, so basically in this proof we've looked at R modules, okay, over a commutative ring R. We looked at certain R modules, and the way we studied that was we passed to certain vector spaces, F of those R modules, okay, using this tensor product which I constructed for you. So you went from R modules to K modules, okay? And the key point which allowed this argument to work is that this F, this procedure for going from R module to K modules satisfied these key properties. So in category theory, we provide the environment where we can talk about things such as this functor F. Okay, so what do we need to talk about this functor F? So the types of things we need is we need to talk about identity morphisms. Okay, you should talk about morphisms, and you should talk about composition of morphisms as well. Okay, and this has to be in both settings, in both the R module setting and the K linear setting. You have a composite of R module homomorphisms here, but here we have a composite of K linear maps here. Okay, so categories are basically environments where you can talk about composition and the identity. In the next video, I'll give you a rigorous definition of what a category is. I hope you enjoyed this adventure in pure mathematics.